Welcome back to G Fun Facts Online. Today we are diving deep into a subject that sits right at the frozen edge of physics. We are talking about friction. In our daily lives, friction is the great enemy of motion. A spinning top eventually falls. A sliding puck on ice grinds to a halt. A pendulum stops swinging. It is the tyranny of thermodynamics, dissipating ordered energy into heat. But for decades, physicists have looked for an escape hatch. They have looked to the quantum realm, specifically to superfluid helium-4, a substance that promises a world without resistance. A world where a molecule could, theoretically, spin forever. But recent breakthroughs, including some groundbreaking experiments from early 2026, have shattered that illusion. We are going to explore the paradox of the perpetual spin, the birth of a new quasiparticle called the Angulon, and how scientists used a laser centrifuge to find friction in a vacuum. Let's start with the stage for this drama. Helium-4. Helium is the second lightest element in the universe, and it is chemically aloof. It doesn't want to bond with anything. But its most magical property reveals itself when you get it cold. Really cold. While every other substance in the universe freezes into a solid block when you approach absolute zero, helium-4 refuses. Because its atoms are so light, and the quantum jitter known as zero-point energy is so strong, it remains a liquid even at 0 Kelvin at atmospheric pressure. But at 2.17 Kelvin, something profound happens. It undergoes a phase transition to become a superfluid. In this state, the atoms lose their individual identity. They are bosons, particles with integer spin, and they collapse into a single quantum state called a Bose-Einstein condensate. This gives the liquid miraculous properties: zero entropy, infinite thermal conductivity, and, most famously, zero viscosity. It can flow through tiny cracks without slowing down. It can climb walls. It was supposed to be the perfect frictionless bearing. To study this, scientists don't use buckets of helium anymore. They use something called helium nanodroplet isolation, or HNDI. Imagine a beam of microscopic droplets, each containing a few thousand helium atoms, flying through a vacuum. As they evaporate, they cool themselves down to a precise temperature of 0.37 Kelvin. These are floating, superfluid cryolaboratories. Scientists can trap a single foreign molecule inside one of these droplets. The droplet acts as a quantum solvent, holding the molecule gently in its center. The expectation was simple. If the droplet is superfluid, the molecule inside should be able to rotate with total freedom, as if it were in a vacuum. There are no thermal collisions to knock it around. It should be the ultimate perpetual motion machine. But when researchers started hitting these molecules with lasers to check their rotation, they found something strange. They saw distinct spectral lines, which meant the molecule was indeed rotating in a quantized way, but the numbers were off. The molecule was behaving as if it were heavier than it actually was. Its moment of inertia had increased. For a molecule like carbonyl sulfide, it was spinning as if it had nearly 3 times its normal mass. This was the first clue that the molecule wasn't alone. It wasn't just spinning in a void. It was dragging something with it. This brings us to a revolutionary concept introduced around 2015 by physicists Mikhail Lemeshko and Richard Schmidt, the Angulon. In condensed matter physics, when a particle interacts strongly with its environment, we stop treating them as separate things. We treat the particle and the cloud of distortion around it as one single entity, a quasiparticle. You might have heard of a polaron, which is an electron dragging a distortion through a crystal lattice. Well, a rotating molecule in a superfluid forms an angulon. The molecule creates ripples in the helium bath, tiny excitations called phonons and rotons, and these excitations dress the molecule like a coat. When the molecule spins, the coat spins with it. That explained the extra mass. The molecule was dragging a cloud of virtual helium excitations, but here is where the story gets really interesting. This Angulon coat is stable, but only up to a point. In a vacuum, you can spin a molecule as fast as you want, but in a superfluid, there is a speed limit. As you spin the molecule faster, its energy increases quadratically. Eventually, the energy of the spinning molecule matches the energy required to kick a real excitation out of the helium bath. The most famous excitation in helium is the roton, which requires a specific kick of energy, about 9 Kelvin, to create. Theory predicted that if the molecule spins fast enough to resonate with this roton energy, the angulon becomes unstable. It stops just wearing the coat and starts ripping the fabric. It sheds real rotons into the droplet, transferring angular momentum to the bath. That transfer is dissipation. That is friction. It is the breakdown of superfluidity. This connects back to a prediction made by Lev Landau in 1941. He argued that superfluidity only works because, at low speeds, it is energetically forbidden to create excitations. You can't just create a wave in the fluid without breaking conservation of energy and momentum. But if you exceed a critical velocity, that protection vanishes. You break the vacuum. you start generating drag. For decades, this was hard to prove with rotating molecules, because we couldn't spin them fast enough in a controlled way. Heavy molecules were too slow to hit the Rotan barrier. Light molecules, like water, were so fast they skipped right over it. We needed a way to control the speed perfectly. Enter the experiment of the decade, published in early 2026 by Valerie Milner and his team at the University of British Columbia. They didn't use a mechanical motor. They used light. They employed a device called an optical centrifuge. This is an incredible piece of technology. It involves combining two laser pulses that are chirped, meaning their color changes over time, in opposite directions. When these pulses overlap, they create a laser field that acts like a pair of tweezers, grabbing the molecule and spinning it. But crucially, this field accelerates. It creates a light tornado that can spin a molecule up to hundreds of billions of revolutions per second in just a few picoseconds. Milner's team took helium nanodroplets, doped them with nitric oxide dimers, and hit them with this optical centrifuge. They acted as a quantum DJ, spinning these molecular records to precise speeds to see what would happen. They looked for coherence, basically how long the molecules kept spinning in unison after the laser was turned off. If the medium was truly frictionless, they should ring like a bell for a long time. At low speeds, that is exactly what happened. The molecules spun coherently, protected by the Angulon shell. But as the researchers cranked the centrifuge faster, pushing the rotation toward that critical Rotan energy gap, the coherence collapsed. The signal died out rapidly. They were watching quantum friction happen in real time. The molecules were rubbing against the quantum fabric of the droplet, pumping their kinetic energy into the creation of rotons and maxons. They even managed to hold the molecules at a constant speed right at the edge of the cliff to measure the drag coefficient of the vacuum. They found that this friction is highly nonlinear. It doesn't behave like air resistance. It peaks exactly where the Angulon theory predicts a resonance with the density of states of the helium. This was the first time we directly time-resolved a molecule, tripping over the quantum excitations of a superfluid. This has massive implications. It bridges the gap between the microscopic world of single molecules and the macroscopic world of fluid dynamics. For instance, if you spin the whole droplet, not just the molecule, you create quantized vortices, tiny tornadoes of vacuum that puncture the fluid. We now believe that a spinning Angulon, if pushed hard enough, might actually nucleate one of these vortices, becoming the eye of a quantum storm. This helps us understand everything from quantum turbulence to the behavior of neutron stars. Neutron stars are essentially giant balls of superfluid neutrons, and their rotational glitches are thought to be caused by the catastrophic unpinning of billions of vortices. By spinning a molecule in a nanodroplet, we are effectively modeling a neutron star in a test tube. Furthermore, this opens the door to ultra-cold chemistry. Since we can now control the rotation and the friction, we can steer chemical reactions with laser precision. We can decide exactly how reactants collide and how they dissipate their heat. We are using these rotating molecules as nanoprobes, using their spectral fingerprints to map the invisible landscape of the quantum vacuum. So the paradox of the perpetual spin is resolved. The superfluid is not an empty void. It is a dynamic, living medium. It grants freedom of motion, but only if you respect its speed limit. The moment you push too hard, the ghost in the machine wakes up, and the frictionless world grinds to a halt. It is a beautiful reminder that even in the deepest freeze of the quantum realm, there is no such thing as a free lunch. Thank you for listening to G Fun Facts Online.